I thank the organizers for the opportunity to speak here. And I want to talk to you today about two works, one with Benoit Dherin from Berkeley, and one with Martin Bordemann, his student Charles Alexandre, and Salim Rivire and myself. And this is going to be about Leibniz algebras. What is a Leibniz algebra? I will be always talking about left Leibniz algebras, so this means that the bracket, Leibniz algebra is a vector space together with a bracket which satisfied the left derivation property. And all my Leibniz algebras will be finite dimensional. And so Lie algebras are a special case of it. In order to distinguish Lie algebras and Leibniz algebras, I will always take the letter G for Lie algebra and H for Leibniz algebra, which is not necessarily Lie. So you all know that G star is a Poisson manifold. With the Kostant-Kirillov-Souriau record. So that goes like follows. When you take two functions on the dual of G, then for any element of the dual xi, you can evaluate the Poisson bracket at xi, and that is just the evaluation of xi on df of xi, dg of xi, and df of xi and dg of xi are linear functions on the dual of G, so they can be identified with elements of the Lie algebra. You take the bracket and you evaluate on xi. Yeah. This gives a Poisson bracket. And so our goal today is to generalize this to Leibniz algebras. And so in order to understand the answer we are giving, I have to tell you the answer for Lie algebras, how to deformation quantize the Poisson manifold G star. And so there are two ways to quantize, at least two ways. These are the ones we are emphasizing today. So on the one hand, you can use the universal enveloping algebra, quotient of the tensor algebra by the usual relations. And what you can do is you just introduce a factor h somewhere in front of the bracket, and then you identify S of G in H via symmetrization, thanks to the Poincaré-Birkhoff-Witt theorem with UGH, and so an element here has to go to the symmetrization of yeah, let's say L. Sigma, no, sigma, yeah, I call this sigma, but yeah, let's say P. So this gives you then deformation quantization in the sense that you have a star product. Let's say P star Q is just, you push them over to U of GH, you multiply them there, and you go back. So this is not really explicit, or it can be computed, but it's at first it's not explicit. And so this is one point of view. This is a point of view where the whole of SG, the whole of the polynomial functions, become an associative, non-commutative algebra by quantization. Yeah, this is one of the two. The P's, yeah, this is, let's say, PQ or omega. Better? Yeah, okay. So this is the first point of view, but there's another point of view about the quantization of the dual of a Lie algebra. Can also think of C infinity of G star H bar as a star algebra. Yeah, so the star operation, so you have a kind of a complex conjugation here, and on you have the exponential elements I over H bar X for X and G, and these form a group. Yeah, this to the with respect to the star operation. And what comes in this group structure is the BCH formula, the Baker-Campbell-Hausdorff formula for elements in the Lie algebra. So so it is clear that deformation quantization for Lie algebra is related to the integration, the formal integration, the local integration of this Lie algebra into a local or formal Lie group, yeah, because of the Baker-Campbell-Hausdorff formula. And so this is exactly what we then try to transpose with Benoit Dherin. There are ways to integrate locally Leibniz algebras into something, into racks actually, into Lie racks. And then we take this idea of defining a star product in this way in order to use the local integration to have deformation quantization of the Leibniz algebra. So what we developed with Benoit Dherin is the following theorem. We we used actually their theory, the theory of Cataneo, Dherin, and Weinstein, which is exposed in several articles, about getting functorial deformation quantization for Poisson manifolds. And this theory is about formal neighborhoods of Lagrangian submanifolds in formal symplectic manifolds. And so we use this theory to get a quantization operator Q such that the star product, but now it's not an associative product, it's a rack product, yeah, indexed by H bar, is gotten by applying the quantization operator to F tensor G. And now, so this is then a quantum rack in the same way as in the second point of view, the C infinity functions on G star were a star algebra, meaning that you have a rack structure on exponential functions, where now instead of the Baker-Campbell-Hausdorff formula, you get the conjugation with respect to the Baker-Campbell-Hausdorff formula. This is conjugation. Or, yeah, with respect to Baker-Campbell-Hausdorff. And so this all shows right away that actually what we get from here is much less rich than in the deformation quantization for Lie algebras. The Baker-Campbell-Hausdorff formula is a very complicated formula, while the conjugation with respect to Baker-Campbell-Hausdorff formula is rather easy and converges for all elements. So you lose some of the richness of the theory. And so you have on the one hand the rack structure on the exponential functions, and on the other hand you have a rack action of this rack on all C infinity functions. So this is what we call in this paper the quantum rack, and this expresses our deformation quantization. And the quantization operator Q is obtained via this theory of this categorical, this functorial deformation quantization process. You take the asymptotic Fourier transforms of F and G. You have a phase factor and integration over those. So the phase factor is related to this formal integration of the Leibniz algebra here. And the asymptotic Fourier transforms just mean that you have a cutoff function in there around the critical points of the total phase, not only the S, but also the factors which come in here. Yeah, and so what you can do then is you have a well-defined procedure of for such an oscillatory integral to expand it asymptotically in powers of h bar, and you can describe the occurring terms by Feynman graphs, and so you get a well-defined quantization procedure with all these terms coming from the Feynman graphs. And so what turns out is that the Poisson bracket we obtain then on C infinity of H star is close to the Kostant-Kirillov-Souriau bracket, but kind of different also. It's you take one you take df in 0 and dg in xi. You take the Leibniz bracket of both of them, and then you put it into xi, and you have a minus sign. Yeah, the minus sign is perhaps not so important, but from our from this formula it drops out. So what is okay? This is the Poisson bracket you get. So this is kind of the deformation quantization of duals of Leibniz algebras by a geometric inspired procedure. And now together with Martin Bordemann we developed an algebraic point of view on the question. And in the algebraic setting we are not working with C infinity of H star but S of H. And so in the algebraic framework, you can have, yeah, perhaps star. In the algebraic framework, you can have a formula describing all of those terms of the deformation quantization at once. Yeah, evaluating once again derivatives of f in 0 and acting with some kind of adjoint action on g and then evaluating in alpha. So these terms are of the same form as the bracket, but kind of extrapolated to higher orders. And so these adjoint actions, they rely on the structure constants of the Leibniz algebra. Yeah. So these are the two theorems I wanted to talk about. So let me start my talk. Perhaps I have to be brief. Yeah, so you want to deformation quantize duals of Leibniz algebras. The structures you get are non-associative. So let me explain to you what racks are. Rack is a set together with a binary operation such that these rackings with object of x are bijective, and you have the self-distributivity property. You call such a rack pointed if there is an element 1 such that x on 1 is 1 and 1 on x is x for all x. So this is then pointed. And you have Lie racks. The structure right is smooth, and these maps are diffeos. Yeah. So on a so let me give some examples for this kind of structure. The first example is a group. On each group you have a rank product which comes from conjugation. And so for Lie groups you get Lie racks. You can also these just conjugacy classes in the group get you an example of a rack, while it's not necessarily a subgroup. And one class of examples I want to emphasize is augmented racks. When you have X a set, G a group, and P from X to G such that a map such that P of X point G is equal to G P of X G minus 1. Then you talk about an augmented rack. So for the moment, yeah, a set, yeah, and G acts on X. So here you don't see the rack product for the moment, but actually the rack product is gotten in a very nice way. You just push down one of the elements and let it act upstairs. Yeah, then you get a rack structure on X. And so one theme of my talk is to that all the structures I will present to you have an augmented analog. Yeah, this is important. Here, for example, rack bi-algebras are kind of a linearized version of a rack, and then you have an augmented analog, which are augmented rack bi-algebras, which you can easily imagine. You take a co-algebra and a Hopf algebra downstairs, Hopf algebra acting on the co-algebra, and you have an equivariant map, yeah, P, sending you the G action to the adjoint action in the Hopf algebra. Yeah, so this is what is an augmented rack bialgebra, and in fact, this bialgebra you get here is augmented. Okay, then why are Lie racks related to the to Leibniz algebras? Because Kenyon showed in 2007 that the tangent space, let's say X a Lie rack, then the tangent space at the distinguished element 1 becomes a Leibniz algebra. Yeah, and such that now you have to add things in order to make it a non-trivial statement. Let me say it orally, such that you get the Lie bracket in the same way as you get the Leibniz bracket in the same way as you get the Lie bracket from a Lie group, meaning you take conjugation, meaning the rack structure in X, you do 2 times this derivative procedure. You first have something which is related to the big add, yeah, map, and then you get to small ad, and the small ad is a bracket. And it turns out that the self-distributivity relation entails for this bracket the Leibniz identity. Yeah. So this is kind of, for us, the most important point why we work with Lie racks. So let me come then to rack bi-algebras, which I kind of explained already to you. So these are co-algebras R epsilon 1 mu. These, co-algebra, and all of our co-algebras are co-associative, co-unital, and co-augmented within element 1. And so together you also take a kind of product, which for the moment is just a bilinear map. And you ask that this bilinear map respects the unit. And now you have three properties. You have the linearized self-distributivity relation. This is the most important one. In Sweedler notation, this is like that. If you don't write the sum, and if mu of AB is written as the rack product, yeah, by definition. So this is a linearized self-distributivity relation in Sweedler notation, and then you have acting on 1 gives you this, and 1 acting on A gives A for all A, B, C in R. So this is a rack bi-algebra. Excuse me? Yeah, I'm sorry, yeah. And then what we do together with Martin and Salim and Charles is that we have also classes of examples applying what we call the Serre functor to Lie racks, get rack bi-algebras. And the Serre functor means you take on the Lie rack you have a distinguished point, and Serre functor means you take the distributions on this manifold with support in this point. Yeah, point-wise distributions on the underlying manifolds, and then you always get a co-algebra, yeah, and the rack structure on the Lie rack gives you this multiplication mu. So we call this Serre functor because Serre, in his book on Lie algebras and Lie groups, used it in order to construct used it to show that the universal enveloping algebra of a Lie algebra can be gotten in this way, yeah, as pointwise distributions on the group. And here in our setting, we get rack bialgebras. So you can play the game. You go to augmented Lie racks, then you will get augmented rack bialgebras. This is kind of just yeah, as co-associative, yeah. So, because all our examples come from manifolds, we don't deform the co-algebra structure. We always stay with co-associative co-algebras. So, we also have a rack bialgebra associated to Leibniz algebra, which is close to the, yeah, it's a construction of a rack product mu on the symmetric algebra of the Leibniz algebra, underlying the on the Leibniz algebra. So, in the last minutes, I would like to tell you how this deformation quantization can be cast in a deformation theory framework, because what we did was we have now a cohomology theory in which these rack bialgebras have deformations, and the deformations are like classically classified by the H1. Yeah, infinitesimal deformations are classified by H1, like in the classical case. So this is my last point. Deformation theory of rack bialgebras. So here we take co-commutative rack bialgebras. And there is already an existing cohomology theory for rack bialgebras in the literature. I should have said that rack bialgebras in somehow this way had been introduced by Carter, Krantz, El-Hamdadi, and Saito. And so they have a cohomology theory for rack bialgebras, but for the moment it works for them only for in degree 1, 2, and 3, while in our framework it works in all degrees. But we have to admit that we are not deforming the co-multiplication, only the multiplication. And yeah, perhaps you can guess what a formal deformation is. This is formal series of these mu products, such that mu 0 is mu we started with, and the whole space becomes a rack bialgebra with respect to the H-deformed bracket, and so when you then take a rack product which you take as some fixed rack product plus t times a co-cycle, and you put it and you write down what it means to be a rack bialgebra, then you easily get the co-cycle identity. And so this gives you perhaps a small glimpse of how complicated these co-boundary operators can get. This is only one co-cycles, yeah. And now the co-cycle, the co-boundary operator in general are really complicated, and but we managed to show that d squared is equal to 0 in general, and as always in this rack context, this is related not to the usual simplicial world, but to the cubical simplicial world. So we kind of have a kind of augmented cubical object, yeah, here, which we are constructing to co-commutative rack bialgebra, such that the H1 in this complex it classifies the infinitesimal deformations of Lie bialgebras. So let me stop here.
Okay, are there any questions? And we've been asked that questioners should use the microphone.
So you mentioned the Poisson bracket. Mm-hmm. Is it really a Poisson bracket? I mean,
no, it's not.
It's not.
It's not a Poisson bracket in the sense that it is a Lie algebra structure and derivation in both variables, and that no, it's not a Poisson bracket in this sense. As you see perhaps from the expression, which is not on the blackboard anymore. It's only a derivation in one of the two variables, and it doesn't even satisfy the Leibniz identity. So it's kind of a very ill-defined Poisson bracket. Yeah, but we are working on extracting interesting properties from this bracket and doing some generalized Poisson geometry with this kind of bracket.
And I guess if you don't freeze the first argument, it's even worse, right?
Don't freeze it.
Because in the formula.
You have 0 of the first.
Yeah. If you put a psi also on the left, is it interesting or absolutely not?
I can only say from our theory, the Poisson bracket which drops out is this one. Yeah, and this is why we didn't consider other Poisson brackets. But I can tell you, even if you put the variable also in the first spot, yeah, and not 0, then you don't get Leibniz identity. You don't get better properties.
And sorry, just a last small question. There are a special kind of racks called quandles when you add an axiom x triangle x is equal to x. Do they pop up in your framework? Or?
No, not really. Okay. Not really, because what we need is self-distributivity identity in order to have on the tangent space of the Lie rack the Leibniz bracket. So the Quandl axiom which could be added does not occur naturally in our theory.
So I'm going to ask exactly the same question as I did when Kassel was talking, and that is, can you define the deformation on on R epsilon. That means when you divide out by h squared. Meaning that, is this really a deformation theory in the classical sense? Is there an idea of deformation of racks on Artinian K-algebras? If you have such a thing, then the maximal ideal of your divided by the maximal ideal squared would tend to be the cohomology that you are interested in.
Mm-hmm, mm-hmm. Yeah, actually, I didn't formulate deformation theory in the sense it was formulated this morning. So we are not deforming on some base. Yeah, but we are, but it's kind of implicit. Yeah. Perhaps I don't really understand the question. Yeah. We are not dividing by an ideal here.
Every Leibniz algebras can be integrated to a Dirac. From a Dirac, you can obtain a Leibniz algebra.
Yes.
Is the converse also true?
Any Leibniz algebra can be integrated into a rack. Yes. Yes.
How about
but actually, kind of in several ways and in many ways, and it's kind of too flabby. The structure is too flabby in order to have a nice theory like in Lie groups and Lie algebras where you have a unique integration. But one way to integrate Leibniz algebra into a Lie rack is to take this formula. Yeah? This is a rack product on the vector space underlying the Leibniz algebra. But yeah, of course, this is kind of not satisfactory because when you think about Lie groups, you want a manifold with non-trivial topological structure. And this is not the case here. But you can render it non-trivial, and Simon Covey's was the first to integrate a general Leibniz algebra into a local Lie rack in such a way that in the case of Lie algebras you get back at least locally the Lie group integrating the Lie algebra.
One last question.
Okay. This rack was invented for node theory so far, and they are related to this quandle mentioned by Dominique. Then my question is, what kind of node theory property we can expect from this?
Mm-hmm. Yes, actually, this is kind of an orthogonal theory to the use of racks and knot theory, because in knot theory what you use is finite racks in order to have counting invariance. Yeah, you want to, at some place you want to sum over all elements in the rack. And in our Lie racks you cannot do that. So it's kind of very different world.
Okay, let's thank the speaker again. Thank you.